Exercise 8D.2, more work on trying to find models for real data, which basically means we get this set of numbers and you try to find an equation for it, a formula for it if you like. And it's easy if it's in a straight line, it's not so easy if it's not in a straight line, and we obviously are doing the ones which are not in a straight line. So here's our question here. We're going to do this. Well, this was one of the ones I didn't get a chance to do in the last lesson video. So it's an exponential one. You can see that because it says a power of x. Now when it's like that, our model basically runs like this. We take logs of both sides, and when you do that you can split it because it's k times the b to the x, so it's log k plus log b to the x, and that allows you to bring the x down to the front because of the power law. So that gives me x log b, and that's equal to log y. Now that's more or less it, apart from we just line these up. Y is lined up against y. The log k, well that's actually the c again. This is the x and this is the m. What this means is that my graph is going to look like this. I'm going to plot log y on this axis, but I'm not going to plot it on that axis. It's going to say x here. So this is an x because you can see they line up. It doesn't say log x, it says x. So I've got a little bit less work to do this time. And when I do it, my y-intercept will be log k, and my gradient will be, so that's my y-intercept, my gradient will be log b. So you can tell a lot from that piece of mathematics we've just done. So we will need to draw a graph. Now these are the numbers I got last time when I did it. I'm not sure if they're true or not. Let's see if I get it. So that's my answer that I'm hoping to get, but it doesn't mean it will be this way. Now I did say I had to, if you remember, I said I have to log the y, but I don't have to log the x. So I'm going to draw a new table of values. The x will stay the same. It will say 2, 6, 7, and 10. But my y has to be logged. So it's the log of 1.74 I'm going to do. So the log of 1.74 point. Again, you can't be too accurate with this. So 0.55 is as good as I'm going to write. The log of 0.76 is minus 0.27. The log of 0.61. What you notice is these are going down, minus 0.49, and the log of 0.42 is 0.8687, I suppose. So there are my numbers. I am now going to draw a graph of those. Now, again, notice going across, make it a relatively easy. Oh, actually, I need to get some negatives, so I'm going to put this here perhaps. And I need to go from simply 0 up to 10. So why don't I just do 0, 2, 4, 6, 8. No, I can't do that. So why don't I do 0, 5, 10. There you go. That was a really simple axis. That's x. And going here, I need to go from 0.55. So why don't I just do 0, 1, minus 1. That's what I mean about when you do this on this math. Don't make it overly complicated for yourself. So hopefully that will give me a straight line when I do it. So 2 across, which is there, 0.55 is there. Minus 0.27 for 6. So 6 is there. Minus 0.27 is about there. I'll soon see if these look straight. 7 is there. Minus 0.49 is more or less there. That looks straightish. And 10 is minus 0.87. That's about there. So it's not perfectly straight, but it's kind of straight. I'm going to try and draw a line of best fit through there. I'm going to try and do it by. I'll pause it and come back. Now, I'll be honest, I don't think that was a very good line at all, but it'll have to do. It took me ages to try and work out how to get that roughly through the right points on this dodgy tablet. So anyway, I reckon that goes through at about 0.9ish. I'm not going to be too accurate. And going down, well, that's handy. It goes down 0.9, and again it goes 5 across. So 5 across to there. So I reckon the gradient is about 0.9 down. Obviously it's a negative, it's down, divided by 5, which is minus 0.18. Doesn't sound very good, but we'll see, I suppose. Let's just make sure I don't make a stupid mistake. So there's my, now bear in mind what we had was I said that the y-intercept is log k. So my log k is 0.9. So my k is e to the 0.9. K equals e to the 0.9. 2.45. It's not as, well, to 1 dp is 2.5. So it's a bit lower than this number here, but bearing in mind my dodgy tablet I'm trying to do this on, the graph paper, it's not a million miles away. Certainly it's not horrendous. And I also said that my m is log b. So my gradient is log b. And what was that? Was 0 minus 0.18. So b is e to the minus 0.18. Just like a dodgy line there. B equals, let's just do that, e to the minus, it doesn't look as if it's going to be right, 0.18. It's actually very close. It's 0.8 to 1 decimal place again. Yeah, it actually is. So that one's much better. If I'd written this, then I would have written y equals 2.5 times 0.8 to the x. And that gives you an indication of how we're meant to do this. So notice now I've now shown you on the 2 videos how to find the constants both on this type, which is the exponential type graph. Exponential being because the power is the x. But we also had ones which were written y equals ax to the n, and here you'll notice the power is not the x, and these are described as being polynomial, and you need to be able to do both types. So get your head around that and make sure you can do both types. Modelling then, we sometimes get given a bit more information rather than making us draw the graphs. They do a lot of the work for us. This could be, another example I've given here is a cup of tea, and how it cools down over time. So don't be surprised when you get these. The reminder then, you could get given this type, the polynomial type, and this is the maths that you're meant to learn. And learn how to do, because I wouldn't necessarily want you to have to do that in the exam and have to invent it yourself, but learning roughly what it looks like is what I'm after. And this type is the exponential type, and again this is what you're meant to be able to do, the rearrangement to get the gradient and the y-intercept in both cases. And also the fact that on this one you draw a graph, and because it says log y and it says log x, that's what we plot on our graph, log y and log x. Whereas on this one it says log y and x. It's a different graph, log y and x, no log in here. You need to know that. And it doesn't matter which one you use. You can use a normal logarithm or the natural logarithm. It's probably easier to use the natural logarithm because on most of your calculators that's the easy button to use. So wordy examples then. Mass of some radioactive material, it seems, is modelled using this, where m is the amount of mass, t is the time, seconds, and with c and b are presumably the constants we were trying to find. A physicist then measures this on the and gets some kind of graph from it, and he plots, or she plots, t on the x-axis and log m on the y-axis. Let's just use our brain. M equals cb to the t. So log m, they've taken to the base 10. If it doesn't say so, it means to the base 10. Log of m equals the log c. Now remember, you split it and you'll end up with t log b. See if you can get that maths out. If you can't, now so this is my y equals c plus x, my variable is the x. So notice I should really plot x with t on the x-axis. Yes, they do. And log m Yes, they do. Now, just looking at what they've told me there, log m equals 1.3 minus 1.8t, and I've said that log m is log c plus t log b. So I think I can just quite easily say my log to the base 10 of c must be equal to this 1.3. You can see that. And it says t log b, and it says t here, and also my log b has got to equal minus 1.8. So just by looking at the two equations, you can see which bit lines up with the other. So my c then, and I've got to move that log to the base 10 of c onto the other side. Now, because it's to the base 10, it becomes 10 to the power of 1.3. And my b becomes 10 to the power of minus 1.8. So in both cases, I just move the log onto the other side, both base 10, so it's 10 to the power. So what is 10 to the power of 1.3? Let's do that now. 10 to the power of 1.3, that is, it says, well, 19.95. It also want two significant figures. That's 20 if I round it to two sig figs. And this one is 10 to the minus 0.18, or 1.8, sorry. So 10 to the power of, what is it, negative 1.8. I get 0.016. Don't know if they're right. Oh, you can just about see them on the bottom there. Yes, they are. And yeah, that's good. Another example then. A scientist thinks the variables x and y are related by the equation y equals ax to the n. So here's our scientist down here. We've got this formula. She collects the data and plots a scatter graph with log x on the... So I just think it's probably useful just to... They're saying log again. So it's log to the base 10 of y equals the log ax to the n. If you remember what we do, well, I'll do it properly this time. That's a time, so it's log a plus log x to the n, and then the n comes to the front. I'll just rewrite it here, log a plus n log x, and that's equal to log y. So again, you line these up. Y equals the m is that one, because this is obviously the x plus c. So the points follow a straight line with gradient 2.6. Well, my gradient then is 2.6. Now notice here the gradient lined up with the n, so I now know straight away n is 2.6. Didn't have to do anything to that at all. And the y-intercept is minus 0.9. Well, notice my y-intercept is log a, sorry, so c equals log a from here. That's minus 0.9, they tell me. So a is 10 to the power of minus 0.9. So if you get the question like this one, where effectively they've done all the work for you, you can be very grateful, because drawing those graphs is painful. So I'm doing 10 to the power of minus 0.9. I get 0.125. 126. What's it want? How many? Two significant figures. 0.13, I think, and 2.6, I think. 0.13x to the 2.6. That's even worked. So we're going to do some of those. So notice there might be a bit of drawing to do. We're finishing off exercise 8D. There might be a bit of drawing to do of graphs. There might be some maths to do where they've done all the work for us, and we are meant to effectively put that into some kind of understanding of how this all fits together. So, okay, thank you very much.